Hello everyone. Today I'll highlight what you want. Weakly-Supervised Instance-Level Controllable Infrared Visible Image Fusion. Our goal is simple but powerful. Allow a user to point, in natural language, to exactly one instance, the car on the right, the person at the top left, and produce a fused IR VS image that highlights that referenced instance while preserving overall image quality. This bridges a long-standing gap between traditional, uncontrollable fusion and practical, task-driven, instance-level control. Infrared imagery is robust in low light and at night, but lacks texture and color. Visible imagery has rich detail, but degrades under poor illumination. Standard fusion aims to combine these strengths, but most approaches are static. They produce one fixed output regardless of the task. Even recent controllable methods tend to operate at the semantic level, all cars, not the instance level, the car on the right. Real applications in surveillance and autonomous driving require the latter. Precise highlighting of the one, user-referred instance that we contribute three main ideas. First, we introduce an instance-level controllable VS, IR fusion framework that responds to free-form text. Second, we adopt a two-stage weak supervision pipeline. Stage I generates pseudo-labels for the referred instance from text. Stage 2 trains a fusion network with region-specific strategies for target versus non-target areas. Third, we design the key components that make this possible. A text-to-image response network, TRN, a multimodal feature alignment, MFA, module guided by manifold similarity between text tokens and image patches, and an instance selection module, ASM, with 12 relative spatial rules, left, top, right, NTH from left, etc., to pick the exact instance without extra annotations. Our pipeline has two stages. Stage I takes an IR image, a VS image, and a text prompt. TIRN produces a response map indicating which pixels correspond to the text. Then ISM parses spatial terms in the text and, using the centroids of candidate objects, selects the one that best matches the relative position description, yielding an instance-level pseudo-label. Stage 2 uses these masks to supervise a fusion network. It enhances the target region by combining IR luminance with VS color/texture, while preserving non-target regions for overall quality and structural fidelity. At inference time, we run only the fusion network. It has learned to localize and fuse from the text. Why does TIRN find the right pixels? The MFA module treats text tokens and image patches as points on their respective feature manifolds. We construct a KNN graph and compute shortest path distances to estimate manifold proximity between text and image features, convert these distances into similarities, and feed them as priors into attention. Intuitively, a text token like car and the patch corresponding to the referred car should lie closer on the joint manifold. MFA exploits this to steer attention weights, improving alignment both ways, text image and image text, and yielding sharper, more reliable response maps for instance selection. Qualitatively, our method does what users expect. If the text says the car on the right, we highlight that car, not every car. If it says the person at the top left, we emphasize that single person. Compared to semantic-level controllable baselines that often brighten all objects of the mentioned class, our system resolves the correct instance and adapts fusion accordingly. Notably, even without text, the model's non-target strategy produces competitive static fusion, showing that controllability does not come at the expense of base fusion quality. Across standard VS, IR benchmarks and widely used metrics, we achieve state-of-the-art or superior performance. This means two things. First, the fused images are objectively strong by classical measures. Second, introducing instance-level control does not degrade global fusion quality. Instead, it improves relevance. Users get the exact emphasis they ask for while maintaining detail and structure everywhere else. Ablation studies confirm the importance of each module. Removing text supervision or manifold similarity makes response maps less discriminative. Replacing MFA with vanilla cross-attention reduces alignment precision. Reducing or removing ISM's 12 spatial rules weakens instance selection. Visualizations further show RIS models designed for single-modality natural images struggle under VS IR conditions, while our dual-modality representation plus manifold-guided alignment handles them well, producing accurate pseudo-labels that drive controllable fusion. Though we also evaluate downstream targeted object detection by feeding fused images into YWLO-style detectors. Because our fusion explicitly highlights the referred instance, especially in low-light scenes, detectors see clearer signals, leading to higher confidence, recall, and map on benchmarks. This demonstrates that instance-level controllable fusion is not only visually interpretable, but also functionally beneficial for real-world tasks like nighttime pedestrian or vehicle monitoring. To conclude, we present a Weakly-Supervised, instance-level controllable VS IR fusion framework that turns natural language prompts into precise instance highlighting. Through TIRN plus MFA plus ISM, we connect text understanding, instance localization, and region-aware fusion in a single pipeline. Experiments show strong fusion quality, accurate instance control, and downstream gains. We believe this opens a path toward broader multimodal, interactive vision systems where users can literally tell the model what to emphasize and get exactly that in the fused result. Thank you.